actually even smaller. So if we can get 16 bytes somewhere, plus shellcode, right, then we can, once again, do the things we want to do and slap AIX around like it doesn't know what it's doing. So the first 4 bytes of our fake frame is going to be a PowerPC branch instruction. So anybody here not familiar with power, RISC architecture or anything like that? I see 0 hands. All right, no, 2, 3, great. 4, all right, 5. What that is, basically, if I can relate it to like an x86 world and then I don't get flamed later, is a call. So you're calling a function, a branch is pretty much the same thing. There is a little bit of differences, and we'll go into that. So the second 4 bytes is required to be a NOP. And I'll go into more detail at the end of the end of this talk, but the reason for that is, so power and RISC and pretty much all the RISC, all the RISC, actually do something called instruction caching. So when you do a branch, it actually executes the next instruction before actually calling and doing and branching out. And so I'm not, let me back up, I am not that smart. I mean, I'm a good old Texan boy that thought we could make this happen. So I can't tell you why that's better, but they think that it makes it faster, and I believe them because I drank the Kool-Aid, I guess. So the third pointer is the pointer to the value we want to overwrite. So this can be a function pointer that points to, so in AIX, the file format's COF or XCOF, and so if you can relate it to L for PE32, there is a list of function pointers that say, oh, by the way, system's over here, and free's here, and malloc here, and string copy's here. We can overwrite this table or hijack one of the functions of the table. So if you can find a function that's called pretty close after we've overwritten this, then instead of going to the real system or the real malloc or what have you, we're actually going to, it's going to execute our pointer, it's going to hit our pointer instead and go to our code. Also, obviously the other way is the good old, overwriting your return stuff on the stack, which typically makes a little bit more sense in some areas. So if you're doing just a demo app, maybe I would either overwrite something on the stack, or I would maybe overwrite exit, because in the end everything exits, and just to kind of give you a good idea of how that works. But in a real life situation, you've got to pick something that's going to happen pretty close and that you can actually leverage pretty well. And so once again, the last 4 bytes is the heap size, and that heap size once again needs to match the size that we already overwrote when we corrupted the data. If we only have 4 bytes of corruption, then we need to make sure that size matches whatever the size is already existing. So you don't have to overwrite the entire thing, you can overwrite just 4 bytes of it, but you've got to make sure that size matches. Otherwise we're not going to get to a certain area code that I feel it's necessary to leverage and take advantage of code execution. There may be other ways without having to get it to match, but the way that, so Litchfield's methodology as well as the methodology that I'm going to be talking about later, both require it to match. Okay, so a little bit of visualization here. I'm not a big picture guy, but I did create this. It's my pretty picture, and it's probably the best picture I've ever made. Once again, beginning of the frame is our branch instruction. So there's different types of branch instructions. There's conditional branch instructions, and then there's just your basic branch ignorantly and go. One of the things with the ignorant branch instruction is it actually contains a null byte. However, so anybody heard of H.D. Moore? I hear he's popular, but so I was talking with him not too long ago, and I actually found some documentation where he's like, oh, but if you change it to, I think, 0x48, then it still works, and it's kind of undocumented because I haven't found it anywhere in any like PPC documentation, but apparently that it is what it is and it works, and I don't know why, and maybe he does, and maybe he doesn't, I don't know, but it still works on Power 6 and Power 7. So I was kind of surprised to see that was still a useful piece of information. If you don't want to utilize that, and or later on down the road Power fixes all that, or it's all fixed by IBM for Power, you could use a conditional branch, and you just need to figure out which condition it's going to be. So if you pick the wrong condition, then obviously it's not going to go to it, right? So you got to make sure you have the right environment for that to occur. Next one's a NOP instruction, once again, because of the caching. The third is location of our function pointer, once again. Stack or a function pointer somewhere. You can also maybe abuse another function pointer on the heap. So, I mean, you've seen the talks for heap spraying and some of the nasty stuff done in the corruption, for example, like in Windows applications such as Internet Explorer and things like that, use after free, where you're basically overwriting function pointers that are already existing on the heap. So C++ objects, when you allocate a new C++ object and there's function pointers in there, that's kind of how that's done. And once again, heap size. So please note at the bottom, I did not do this image. This came directly from Litchfield's paper. So David, don't come after me. I'm giving you credit, dude. You'll see that I mentioned the bidirectional double 4-byte overwrite, and I'll kind of explain his image a little better because it kind of looks convoluted, but it makes complete sense to me. So you're seeing that they're being swapped out. So we have both. So this one is a little bit more complicated. So we have both values, but the values also have to be valid memory addresses because they're going to get messed with also. And basically, wherever we're overwriting at, they're going to swap that data with the data with our fake heap frame, and we don't care anyway because it's malicious and it's doing what we want to do, and we're not going to reuse that ever again anyway. So, got any questions before I go on? Sweet. All right. So I'm a bad coder. I wrote a really bad function, and this function allocates 20 bytes. And then we copy, and it's uncontrolled, however much data it passes as an argument to this heap segment that we just were given to us by the AIX Heap Manager. And then we free it and then return. So what that does is we have corruption in the middle. You'll see I've highlighted that. And then it's going to be freed. And so what happens is the AIX heap management is going to go, okay, well, let me walk this linked list to the right. I was going left, and that's the wrong way. So it goes down to the right, and as long as the heap size matches the same, it's going to keep walking this list. But as soon as the heap size changes, then it's going to do something else. And like I said, that else, I haven't done too much research on it, but the else might be leverageable in some way, but we're going to focus on leftmost and rightmost. So within leftmost and rightmost, where it's kind of pretty much the same thing, but it's going to allow us to do the 4-byte overwrite. As I mentioned, I do document the correct pointers to hijack, and so I feel like it's necessary to document this a little bit better because this does not apply to the next methodology. This is only for the Litchfield methodology, which once again saved linked registers, callable functions in the applications export list, and then function pointers found on the stack or heap. Their function pointers may or may not be common. You just got to have a better idea of what the application is doing and how you can leverage it. And so that's why it takes learning PPC, and you got to reverse engineer and all that. Oh, look. All right, so now we're at the new methodology. So once again, any more questions before I go on? Sweet. All right, I must be talking great. So this next methodology, so in the past when we free a buffer, then it uses the rightmost, and it has to walk this double linked list that manages the heap elements to the right. When you malloc after corruption, it actually goes left to add it within this double linked list, so it's all contiguous. Yeah, that's about it. All right, I got nothing. When we're unlinking an entry and linking an entry, we're walking through, and when we see, when the algorithm sees that a size matches and it's at the end of this type of match, then what it's going to do is it's going to insert this element, the new element, into our linked list, and it's going to make sure it's there. And so this is how we're able to take advantage of this. Like I mentioned before, when it may be possible in the other routine, but this is pretty basic. It's your basic 4-byte overwrite, and Once again, I'm lazy, and KISS, keep it simple, stupid. So I just kind of took it and ran with it. So with the new methodology, a lot of it's the same. We do have to have a controllable piece of information, controllable piece of data. So whether it's on the heap or if it's on the stack, or if you find some new location to put it that nobody knows about, awesome, good for you. The only difference is, so in the past when we needed 16 bytes, this one we only need 8 bytes. So an example for like some sort of proprietary protocol where maybe there's 4 or 8 bytes of a reserved something that's not being used, we can maybe pad it there. So example, RPC might be a good example for that. If it's ASCII protocol like FTP, then who cares? You can do whatever the heck you want. But some of the proprietary protocols that AIX likes to really take advantage of and love to death, that's kind of where we're going to start focusing a little bit more. And the reason I feel like it's beneficial for that it's only 8 bytes in this next one is obviously you can sneak this in just a little bit easier and do the things you need to do. So when we overwrite our 8 bytes, which is the same 8 bytes, we're saying 4, but actually no. So this one you have to overwrite 8 bytes. You can't take advantage of the heap size on this one. So the size does matter in this. The first 4 bytes is going to be the same thing. It's the location of our fake heap frame memory. So same location. However, the difference is our heap size is actually the value we're going to overwrite, because what it's doing is it's saying, oh, by the way, this is how big it is. And when we take advantage of that, it allows us to do some pretty funny stuff, and I'll show you a demo here in a bit. So pretty much same slide. I got to use the same image over again, but what I did is actually there's a minute change, and if you can see it, let me know, because I can't see it from here. So same buffer size, 1024 bytes. And then right after this piece of heap element, the next heap frame is going to be adjacent to it. And so if we can overwrite this header, once again, the difference is the function pointer ends up being, or the pointer we want to overwrite is the actual size, but it's size minus 12 bytes. And so if it were 41, 41, 41, 41, you'd have to subtract 12, which I can't do math. I didn't teach that in Texas, so we don't know, but you can figure it out. So when we created our heap frame in memory, once again, it's an element of a linked list. It does require a controllable location of memory. Writing the 8 bytes, writing 8 important bytes, I'm glad I highlighted that, has to contain our unique structure. It's technically the same 16 bytes structure for leftmost and rightmost. However, we only need 8 bytes of it, so we don't care about the last half of it at all. So kind of a little bit of a review. With minimal heap corruption, we're able to take control of exactly what we're trying to do. It is complete code execution, and it does take only minutes to write. So, everybody likes the basic Stack Overflow where you're like, oh, EIP or PC is now my magic number and now I can do anything I want with it. Well, this is pretty much the same thing. The only additional research you've got to do, apart from aligning things, which we'll talk about a little bit more, which is a pain, is also you've got to find the right pointer to overwrite. Once again, so I suggest always start looking at the stack because it tends to make the most sense. Oh, actually, so side note, anybody here heard of ASLR? Address space layout randomization. Yay. Guess what? AIX has never heard of it. And nobody else at IBM, apparently, I mean, I know they have because what's his name from IBM just spoke about all this stuff, but I guess they're on 2 different teams and they need to, cross-educate just a little bit more. So, a part of, one way I might dread giving this talk is now that IBM is very familiar with both methodologies being used, they might decide to fix it one day. So that'll screw up all the fun things I have going for this. So, another thing they've never heard of is heap cookies. Anybody know what a heap cookie is? So what a heap cookie is, when an application starts up, it randomizes a value and it stores this value in memory, and every time it creates a new heap value, or